Hello and welcome to the first set of tutorial solutions for 9120 Mechanics for Teachers. So if you're wondering why Liz's voice has suddenly changed, well, that's because this isn't Liz speaking. My name is on the screen. I'm Bryony Lanigan. I graduated from the UNSW School of Physics in 2017 after completing my honours in condensed matter physics under the tutelage of Michelle Simmons in the Center for Quantum Computation and Communication Technology. So now you know who I am, let's move on to something a little more important, which is the physics. So while this particular module was a little bit shorter than the ones to come, it's very important that you understand vectors because that is the backbone of mechanics. Everything that we do from now on will be using vectors, and so if you have any questions, please ask them now because it's very, very important that you are able to work with them mathematically as well as conceptually. So let's start with question 1. So the first question here asks us what is the difference between a scalar quantity and a vector quantity. So the difference between them is a vector quantity has both a magnitude and a direction, while a vector quantity has a magnitude and direction, while a scalar quantity simply has a magnitude. So this is very important distinction, and you'll see it comes into play a lot later on. Yes, this is a very important distinction, and you will be working with both scalar and vector quantities in future courses, so it's important that you are able to distinguish between the two. So our next question is, so in some cases the displacement and the distance. So displacement is the vector quantity of vector analog of distance, which is scalar. And so in some cases they are the same in magnitude, in other cases they are not. So one case where they are the same in magnitude is if we were just finding the distance between the straight line distance between 2 points, say A and B. So the displacement, if it's just a straight line, will just be the distance between A and B, and well, as I just said, the magnitude of the displacement is the distance in this case. However, if I were to start at a point, go around a circle, and then come back to that point, then my displacement is the difference between my start and my end point. We can see here that my start and my end point are the same. So my displacement, the magnitude of my displacement, which is represented by the absolute value of our vector s, is 0, but our distance will be equal to 2 pi r. And the r is the radius of the circle that I walked. So we can see here the displacement, well, the magnitude of the displacement will equal the distance, but here they will be two different things. Okay, so on to question 2 now. So if we are given these three vectors, we're given A, B, and C in IJK notation, then we are asked to evaluate A plus B, B minus C, and then finally A plus B minus C. So I'll start off by writing out A, B, and C. So just a note about notation here. I am noting vectors by writing a letter and then putting a little arrow like that over the top. So it's just a notation difference. That's no different to me writing a vector with a little squiggle down the bottom, or even some people even write both. often with these things called unit vectors, the I, J, and K. You can write them, they're often written with both. However, I signal them by putting a little hat over the top. Just a little notation note there. Let's go on to the questions. So question A is just A plus B. So when we are adding two vectors that are in I, J, K notation, it is as simple as adding the I components, adding the J components, and adding the K components. So this will become 4.5 plus minus 2.0 I, because see I've got a minus here, plus, and then we have 5.0 plus minus 3.5 J. And then I'm going to write plus again, because then let's go plus minus 1.0 plus 3.0 K. So this just becomes minus there. So it's 4.5 minus 2.0, so that's 2.5 I. 5.0 minus 3.5 is plus 1.5 J. And then minus 1.0 plus 3.0 is plus 2.0 plus 2.0 K. Okay, and then part B, B minus C. So B minus 2.0 minus 1.0 I. So this is why I was doing the plus minus there, because that way if we're subtracting vectors, we're still making sure that we're not getting our signs mixed up. Plus minus 3.5 minus, it's positive, so I won't bother writing it, 2.0 J plus 3.0 minus negative 2.0 K. So going through, so this cancels out, becomes a plus, stays as a minus, this becomes a plus, and we end up with negative 2.0 plus 1.0, that's minus 1.0 I, minus 3.5 minus 2.0 becomes minus 5.5 J, and 3.0 plus 2.0 is plus 5 plus 5.0 K. Okay, so for part C, there's two ways we can go about this. There's many ways we can go about this. We can go about it just by starting from scratch, going, well, okay, 4.5 plus minus 2.0 plus minus 1.0, and going through that. Or we can go, well, A plus B minus C. We've already got A plus B here. It's this. And we know what C is. We've got it right here. So we can just take this vector right here and subtract C from it. So let's just do that, because I think that's a bit easier. So we have 2.5 minus negative 1.0, because remember it's minus C, I, plus, and we got 1.5 minus 2.0 J, plus 2.0 minus negative 2.0 K, that wasn't a very good K there, equals 2.5, becomes a plus, so it's 2.5 plus 1.0, which is 3.5 I. 1.5 minus 2.0 is minus 0.5 J, and this becomes a plus, so it's plus 4.0 K. Okay, so on to question 3, where we're given a pair of vectors, either in magnitude and bearing form or in component form, and we're asked to find the resultant vector in both forms. So for this one, start obviously with question part A. And we are given these vectors in terms of their magnitude and their bearing. So 8.2 kilometers south and 0.5 kilometers east. So I am terrible at drawing. I used to think that drawing out diagrams was terrible and I would avoid it if I could. But in physics, you really can't avoid it. And when it comes to vectors, it is honestly the best way to get it straight in your head. Even if you're terrible at drawing, even if you sometimes find diagrams not so helpful, it is always, always, always necessary to draw a diagram first. So let's do that. We'll start off by drawing our 8.2 kilometers south. Doesn't need to be perfectly to scale, but just going with the standard convention of north is up, south is down, etc. So this is magnitude of 8.2 kilometers south. And then we're told the next vector is 0.5 kilometers east. So a little, tiny little one there. So that means that our resultant, adding vectors head, tail, will go like this. It's not my best drawing, but that's fine. So to find this resultant vector, we can see here that these two vectors are at right angles because one is pointing south, one is pointing east. So that means to find the magnitude of this vector, we can just use Pythagoras. So I'm just going to call it C, so we can just go C is equal to the square root of 8.2 squared plus 0.5 squared. I'll extend that out there. And so that is equal to actually 8.2 kilometers. So we see here we are only given this to two significant figures. So it's actually 8.22 or 8.21, something like that. But because we're only given it to two significant figures, we just have to write 8.2 kilometers. Okay, so now I need to find the angle. So I am given the everything else in terms of like south and east. So it's best if we use the bearing. In fact, we're told to find it in terms of the magnitude and the bearing. So I draw a little bearing compass here. What I need to find is this angle here. So this angle, which I'm going to draw these bits in blue, here, that's 90. That's easy. Now this little bit here is what we want to find. Now if we use our alternate angles rule, because this is parallel to this, we can say that this angle here is equal to this angle here. So all we need to do is calculate this angle in here using Pythagoras, sorry, not Pythagoras, using trigonometry, and then we're all good. So this angle in here, we can see angle here. We know the side opposite to it, and we know the side adjacent to it, so we can just use tan. So tan of this angle is equal to the opposite, 8.2 over the adjacent, 0.5. So the angle is equal to the inverse tan of this, which is 87 degrees. So that means that if this is 87 degrees, then this whole big angle here will be 87 plus 9. So I'm going to call this, or we'll just stick with C. A resultant vector is has a magnitude of 8.2 kilometers, directed 90 plus 87, that's 177 degrees true. That would be the bearing. So now I want to find this in component form. And in fact, this one is really, really easy to find in component form. So we want to convert this to IJ notation. So we know that in IJ notation, I is the horizontal component, and J is the vertical component. So looking at this here, we actually, in the question, we are already given the horizontal and the vertical component, because we're told it's 8.2 kilometers south and 0.5 kilometers east. So we don't even need to do any calculations. We can just write C is equal to the vertical bit is 0.5, 0.5 I, and then it's south, so it's negative 8.2 J. Okay, so part B we can do on this page too. I think we'll probably need to start a new page for parts C and D. For part B, we are given them in component form. So we get A plus B, where A is equal to 0.8 I minus 0.2 J, and B is equal to 0.4 I plus 1.2 J. So the resultant of these will be a plus b. So we'll find this one in component form first because we're given it in component form. So this will be 0.8 plus 0.4 I plus negative 0.2 plus 1.2 j. So this will just be 1.2 I plus 1.0 j. So that is it in component form. Now I want this in magnitude and bearing form. So the magnitude of this vector, if we remember over here, when we drew this diagram, we found that when we drew it with the horizontal component and the vertical component, then we can just use Pythagoras to find the magnitude of the resultant. So what we can do is we could draw this out as this is the horizontal component, this is the vertical component, so the magnitude of it will just be the length of this, which we can find using Pythagoras. So the square root of 1.2 all squared plus 1.0 all squared, and that is equal to 1.7 once again to two significant figures. So if I want to find the angle, then I can once again use trigonometry. So ordinarily I would be wanting to find the angle from the horizontal. That's often what you want to find, but in this case we're told to find the bearing. So that means we need to take the angle from the vertical here. And so this angle is the same as this angle in here. And here this is the j component, and this is the I component. So this angle here, which I'll call theta, you can see is equal to tan of the I component over the j component. So tan theta is equal to 1.2 over 1.0. So that means the angle itself is equal to the inverse tan of 1.2 over 1.0. So this is equal to 50 degrees, two significant figures. So you could also write that a plus b has a magnitude of 1.7 directed 50 degrees t. Okay, so now we need another page, as you can see here. Okay, so now we've got a new page. Let's go to question 3c. So now we're once again given it in terms of magnitude and bearing. However, this time we're not just given south and east, we're given something that is pointing northeast and then something at a bearing of 138 degrees true. So we are no longer going to be able to use right-angled triangle rules for this one. But let's start off by drawing a diagram. So we need something pointing roughly northeast, so 7.50 kilometers. And I'm also going to draw in this angle here, because we know that that will be 45 degrees if it's pointing northeast. And then the next bit is 2.25 kilometers at a bearing 138 degrees true. So if I draw again a little bearing thing in here, 138 degrees is a little bit over halfway between east and south. And I'll just draw it like this. Okay, cool. And now I'll just draw in my resultant, which will be roughly there. Okay, 2.25 kilometers. Okay, so we're not using a right angled triangle, or at least we don't know we've got a right angled triangle. So let's first of all see what kind of triangle this is. So this kind of looks like it could almost be a right angle. It's not, and you can see from the fact that we have something pointing northeast and the next one pointing 138 degrees true. So let's find out what the actual value of this angle is if it's not 90 degrees. So this is 45 degrees in here, which means by our alternate angle rule that this here is 45 degrees. We know that each quadrant is 90 degrees, so that means that this little bit in here is also 45 degrees. Okay, so we know that this whole thing here is on a bearing of 138 degrees true. If this is 90 degrees, that means that this little bit in here has to be 138 minus 90, which is 42 degrees. So if, sorry, it's not 42 degrees, it is 48 degrees. My mistake there. So that's 48 degrees in here. That means that this angle in here has to be 90 minus 48 degrees, or 42 degrees. So finally, we can add these two angles here and get that this angle here is 87 degrees. Now that was quite a few steps, but it's pretty simple angle rules that I'm sure you are capable of, and I'm sure many of your students have seen 1,000 times over in maths. So now looking at this, I'm going to change to a different pen color so we can circle what's useful. We know one side, and we know another side, and we know an angle in this triangle here. So even though it's not a right angle triangle, because we know two sides and one angle, and we're looking to find the magnitude of this side here, which we can just call A, we can use the cosine rule. So the cosine rule states that a squared is equal to b squared plus c squared minus 2bc times cosine of a. So substituting our values in, we just get 7.5 squared plus 2.25 squared minus 7.5 times, minus 2 times 7.5 times 2.25 times by the cosine of 87 degrees. Then we end up with 59.55, but we need to find the square root of that. And that is 2, 1, 2, 3 significant figures, 7.72 kilometers. Okay, so now I want to find the bearing that this is at. So to do that, I need to find this little angle in here. I'm going to do it in red. This little angle in here. So far we've used the cosine rule. So we're going to employ our other non-right angled triangle rule, which is the sine rule. So the sine rule is that sine A over A is equal to sine B over B, where big A is the angle opposite the side little a, big B is the side opposite little b. So in this case, we're looking for this angle here, so the side we'll be using is 2.25 kilometers. So that means we can write this as sine of, let's just call it alpha over 2.25 is equal to sine of 87 over 7.72. So doing some rearranging, you end up with alpha is equal to sine, inverse sine I should say, of 2.25 times by sine 87 over 7.72, which means that alpha is equal to 16.9 degrees, 2, 3 significant figures. So therefore, A has a magnitude of 7.72 kilometers directed. Now, to find the true bearing, we need to go from the vertical down to this angle here. Well, we know that the angle to this side here from the horizontal is 45. So if the angle from the horizontal is 45 and the angle from the vertical is 45, so this is 45, that means this whole thing here is 45 plus alpha, which is just 61.9, directed 061.9. degrees true. So now we want to find the components. So to find the components, what we want to do is we want to, first of all, we'll draw a diagram. So we've got just our vector A. And now we want to find the vertical and the horizontal components. So we know this angle here, it's 61.9 degrees. And we know this side here, it's 7.72. We know this is a right angle. So using trigonometry, we know that the vertical component is just 7.72. Just going to write magnitude of A times the cosine of the angle, right, theta, and this is the sine theta, and that's the horizontal component. So just plugging that into a calculator, you end up, so you get A is equal to 7.72 times the sine of 61.9 I plus 7.72 times the cosine 61.9 J. Just do this. Plugging that into the calculator, you end up with 6.81 I plus 3.64 J. Okay, it looks like we need even one more page for part D. So for question 3, part D, so for this part we don't need to find the magnitude and bearing form, and that's because you've been given a 3-dimensional vector here. You'll notice if you look at it carefully, we have A is equal to negative 2.0 I plus 3.5 K, and B is equal to 4.5 J minus 1.5 K. So if we go through and if we say that the I component is red, the J component is blue, and the K component is orange, then we can see that there's only one red component, and there's only this does because part B, because vector B does not have an I component. However, it does have a J component, while vector A does not. However, they do both have a K component. So that means that when we add these together, A plus B, you end up with minus 2.0 I, and that just stays the way it is because we're not actually adding anything to it, plus 4.5 J, because that's in the J component. Then you have to go plus 3.5 minus 1.5 K. Because really it's as though there is a little plus 0 J here and plus 0 I. So we don't need to include it when we do our writing out. It's just if you get a bit stuck in your head as to why we're still including an I and a J component, that's why. Okay, so then this works out as negative 2.0 I plus 4.5 J plus 2.0 K. Okay, so question 4. So question 4, we're told, given the magnitude and direction of 2 forces, and the information that the vector sum of 3 forces is 0, we need to find the magnitude and direction of the third. So we're even given a nice diagram to start us off here. So don't worry if you're thinking, hang on a second, I thought we weren't doing forces until module 3. We're not. This is just a bit of context. You don't need to know anything about forces past the fact that they exist, and even then you don't even need to know that. They're just a nice name because they're a really useful vector quantity that we'll be seeing a lot more. So first off, let's draw our F1, magnitude of 21 newtons. We're told it is 30 degrees away from the vertical. We're told that it has a magnitude of 21.0 newtons. We're told F2, that's not a very good one, I'll draw that again. There we go, that's a bit better. F2, which has a magnitude of 15.0 newtons and is directed along the x-axis, so that's just, I guess, horizontally to the right. And then we want to find F3 here. So first up, we want to find what this, what the magnitude of F3 is, because that's normally the best way to start. So to do that, we're probably going to want to have a bit more information. Often because we know the magnitude of two vectors, we know two sides of the triangle. So once we get the angle that is opposite F3, we can just use the cosine rule. So really we want to be trying to figure out what this angle is here. So if we have a think here, if I were to draw a horizontal line here, because this vector is 30 degrees from the vertical, that means it is 60 degrees from the horizontal. So that means using our alternate angle rule, this is 60 degrees. So now I know two sides and an angle, I can use the cosine rule. So I can go F3 squared, actually the magnitude of F3 squared is equal to 21.0 squared plus 15.0 squared minus 2 times 21 times 15 times by the cosine of 60 degrees. So this equals 351. So this is a really nice round number. There's no decimal places, which is because, as any maths teachers out there will have immediately recognized, cos 60 is actually just a half. So this is actually just 21 squared plus 15 squared minus 2 and 1 half cancel 21 times 15. That's not necessary to know, just kind of an interesting coincidence. So that means that the magnitude of F3 is the square root of this, 351, which is 18.7 newtons to 3 significant figures. Okay, so now I know the magnitude, I want to find the direction. So all of these are given in terms of their direction from the from an axis, and you can see in the diagram we've given you a little angle theta to show you which angle we mean. So we want to find the angle between the horizontal and F3. So that's this angle in here. So to do this, we're going to use our other non-right angled triangle trigonometric rule, and that is the sine rule. So the sine rule is, of course, sine A on A is equal to sine B on B is equal to sine C on C. So this angle here, the side opposite to it, is 21.0 newtons. So I can use this and F3 and 60 degrees to find theta. So another way of writing this, can write sine theta over 21 is equal to sine 60 over 18.7. So just doing a bit of algebra, leave it off, you get inverse sine of 21.0 sine 60 over 18.7, and you end up with 76.5 degrees. So therefore, I can say that F3 has a magnitude of 18.7 newtons directed 76.5 degrees below, spell things correctly, below the x-axis, I should say below the negative x-axis. Okay, so question 5. So we're told a vector points at an angle of 35 degrees above the horizontal, has a y component of 62.1 meters, and we want to find the magnitude of the vector itself. So let's draw a vector here, let's just call it V. We know that it is inclined at 35 degrees, and we know that it has a y component of 62.1 meters. So looking at this, we have a right angle triangle, we know one side and we have the angle, so this just means we can just use trigonometry. So we know this is our angle, this is the opposite, and this is the adjacent. So sine of 35 is equal, sorry, not the opposite, this is the opposite and this is the hypotenuse. This is equal to 62.1 over V. So this means that V is equal to 62.1 divided by sine 35, which is equal to three significant figures, 108 meters. Okay, so now on to question 6. So question 6, we're given the scenario of a pilot flies in a straight line from Vectorville to Conical City. So during this flight, she travels 872.0 kilometers north and 1,305 kilometers east. So she then flies from Conical City at a bearing of 12 degrees to Trigonometric Town, which is a distance of 1,009 kilometers away. And we have several questions. What is the distance between Vectorville and Conical City? How far north of Conical City is Trigonometric Town? And finally, what is the distance between Vectorville and Trigonometric Town? So while there is no part of this question that explicitly asks us to draw a vector diagram, we're going to draw a vector diagram. So let's start off. Okay, so we know that we're going to be heading north and east. So let's start drawing our diagram maybe down here. So like this maybe. So we can say that she went 872 kilometers north. So this is 872 kilometers. And she went 1,305 kilometers east. And then she flew on a bearing of 12 degrees. So I'll draw a little bearing thing here. 12 degrees is very much almost north. And she flew 1,009 kilometers, so going all the way up here. So we'll say here is Vectorville, which we'll mark with a V. I will do that in green. And then Conical City, which I'll just mark with a big C. And then finally to Trigonometric Town, which I'll just call T. Okay, so this is a distance of 1,009 kilometers. This little thing in here is 12 degrees. Okay, so what is the distance between Vectorville and Conical City? So that's this distance here. Well, that's easy enough to find out. We just need to use Pythagoras. So let's start off up here. So this distance, so we'll just go dVc. For the distance between Vectorville and Conical City is just using Pythagoras, because our north and east components make up a right-angled triangle. So 1,305 squared plus 872 squared. So that equals to 4 significant figures. We're given 4 significant figures in this question, which is a nice change. 1,570 kilometers. Okay, so far so straightforward. So part B. So how far north of Conical City is Trigonometric Town? So we know that Conical City is 1,009 kilometers away, but how far north is it? So that means we need to find the northern component of the vector that traces the path between Conical City and Trigonometric Town. So that's simple enough. We're given the angle to the vertical as 12 degrees. So that means using trigonometry, we can see this side is the adjacent side and this is the hypotenuse. So that means that the cosine of 12 degrees would be the northern component of the distance between Conical City and Trigonometric Town. So I'm going to go dCt and then just brackets n for north divided by 1,009. So rearranging and evaluating, we end up with 987.0 kilometers. Okay, so part C. What is the distance between Vectorville and Trigonometric Town? So that will be this distance here. which I'm not going to draw in fully because my drawing is messy enough as it is. I should probably have drawn this a little bit bigger. So I think this shows that you can never draw your diagram too big. So this is obviously quite clearly not a right-angled triangle. So we're not going to be able to use just normal vanilla trigonometry. We have to use our trigonometric rules such as the cosine rule and the sine rule. So as usual, we probably want to start by finding this side here using the cosine rule. So we know the length of this side, the distance between Vectorville and Conical City, which we found in part A. We're given the distance between Conical City and Trigonometric Town, and so now we just need to find this angle here. So you can see this angle is made up of several parts. So we have this little bit here, it's 12 degrees, which we know. We know this here is 90 degrees because it's just between north and west. And now we need to find out what this angle here is. So using our triangle rules, we know that this is equal to this angle here. So I'm going to call this angle little alpha. Actually, I'm going to use a different color so I can draw a little bit bigger. Use that. So little angle alpha here. And this is angle alpha here as well. So we can see that this angle can be found using this triangle by going, well, we have the opposite and the adjacent, so we can use the tan ratio to find that. So tan angle is equal to opposite, 872.0 over the adjacent, 1305. So it's the inverse tan of this. And that is equal to 4 significant figures, 33.75 degrees. So that means if this is 33.75, this is 90, this is 12, then this big angle here, which I'm going to call theta, I'll call theta. Theta is equal to 12 plus 90 plus 33.75, means that it is equal to 135.8 degrees. I'm not sure what happened there. 0.8 degrees. Okay, so now I want to find, now I can use the cosine rule to find this angle here. So the distance between Vectorville and Trigonometric Town squared is equal to this side squared, so 1570 squared, plus this side here, 1009 squared, minus 2 times 1570 times by 1009 times by the cosine of 135.8. And that is equal to some number I don't want to write. So taking the square root of that, we get that the distance between Vectorville and Trigonometric Town is to 4 significant figures, 2,399 kilometers. Okay, so question 7. So we're told that an experienced hiker starts walking down a trail at a pace of 6 kilometers per hour due east for 70 minutes. They then turn and walk north for another 41 minutes before stopping for lunch. And so we're assuming that throughout the entire question, they managed to keep up this speed of 6 kilometers per hour. I guess that's why they're an experienced hiker rather than just your everyday hiker. So one of the things to watch out for in this question is to make sure that you are keeping track of units. Because we can see here we've got a couple of different units. We're given the pace in terms of kilometers per hour, but we're given the time that they're spending in minutes. So have to keep an eye on the ball there. First of all, so our first question is in fact to draw a vector diagram representing the hiker's path so far. So let's start off with that. So we know that they went due east for 70 minutes, 6 kilometers per hour, so we'll go there. And then they went north for another 41 minutes. Let's go up here. Okay, so I want to be able to label this a little bit more. So let's figure out how far they went in this first bit, which I'm going to label with the, I'm going to label it with the blue as section 1. Okay, so for section 1, so they distance, so speed is equal to distance over time. So distance is equal to speed times time. So the distance they traveled in part 1 is equal to, they went going at a speed of 6 kilometers per hour, and they spent 70 minutes. So to convert minutes to hours, we divide by 60, so that's divided by 70, divided by 60, and that is equal to 7 kilometers. Cool. We'll label my diagram accordingly. Okay, and now let's do part 2, and I'll label that in orange, because I can already see there's several more parts of this question. It's a good idea to maybe use color to begin with. So part 2. And so again, the speed is distance over time. So distance is equal to speed times time. So that will be 6 times by 41 over 60. And that is just equal to 4.1 kilometers. I'm actually going to move that a little bit so it's not in my way. And so I'll write that on my diagram right. So I'll write that on my diagram right here. Okay. So here's what we know of the hiker's path so far. So far, I guess we could draw in very faintly. That is their displacement so far. And so it's good because the next question is asking us what is the hiker's displacement and what has their average velocity been over the morning. Okay, so part B. So their displacement, we can just use trigonometry because they went due east then north. So their displacement so far, I'll use D, 1, 2, because so far this is part 1, path 1 and parts 1 and 2 of their path. There we go. Is equal to square root of 7 squared plus 4.1 squared, which is just equal to 8.11 kilometers. Okay, so that's the distance they've traveled, but for it to be displacement, we also need to find the angle at which they went. So we're given this in terms of due east and then north. So we can find, I think it's probably best if we find this in terms of the bearing. So let's draw a little bearing sign right here. We want to find this angle here. So again, using similar triangles, using alternate angles along parallel lines, we can see that this angle is the same as this angle up here. And so that means that this angle here, we'll just call it theta. You just use the tan rule, not the tan rule, sorry, just the tan ratio, opposite over adjacent. So angle is just inverse tan of the opposite, 7 over the adjacent, which is equal to, sorry, not 30.4. Which is equal to 59.6 degrees. So therefore, hiker's displacement is 8.11 kilometers at a bearing of 059.6 degrees true. Cool. Okay, so now we also want to find their average velocity. So average velocity is just the total displacement, so it'll be d12 over the time, and we know that they took 70 plus 41 is 111 minutes. So that means we obviously have to convert that to hours if we want to give it in terms of kilometers per hour, which makes sense because that's how we're given all of our speed in question. So this would be 8.11 divided by 111 over 60, and that is just 4.38 kilometers per hour, and it will be in the same direction as the displacement, so at 059.6 degrees. True. Okay, so then we're told some more information, told they then spot an interesting looking path and follow it for some time, then turn and walk southwest for another 1.5 hours, ending up back where they started. So we need to update our vector diagram to include this. So we want to know what was their total displacement. Okay, so we know that they went in some direction. Let's just say they went this way. They then turn and walk southwest. So actually I'm going to change that. I'm going to have this go a little bit more north, and then have them turn southwest. So it will be this way, and they walk back to their original position. Okay, so they walked another 1.5 hours here. So this distance here then, which I'm going to label this bit as part 3, and then this bit as part 4. So for part 4, I'm going to put down here, then their distance will be 6 times by 1.5, which is just 9 kilometers. So that's 9 kilometers. And because it's southwest, we know that this angle here is 45 degrees, same as this angle here. Okay, so we want to find out now what was their total displacement. Well, that's easy. They went back to where they started, so that means that their total displacement, which I will write here, so part C, total displacement is 0. Okay, now we want part D. So part D, we want to know what direction did the hiker turn in after lunch, and how far did they go before they turned southwest and returned back to where they started. Okay, so actually the easiest part of this is going to be finding the distance that they traveled. Well, it's not the easiest part, but the part that's easiest to find given the information we currently have. So I'm going to need a little bit more space. So what I'm going to do is I'm just going to erase some of what we have because we've got it written down. So I'm just going to get rid of this and maybe all of this here. Always manage to miss some things whenever I try to do this. Okay, so part D. So I know that D1 plus D2 plus D3 plus D4 equals 0. They're all vectors, so I've got to give it all this. So the vector sum of these 4 distances is going to be 0. When we have 3 vectors, we have all these nice triangular rules that we can use. We have trigonometry, we have the non-right angled trigonometric rules. However, when we have 4 distances, it becomes a little bit more difficult to apply those. And so instead, it's often better to convert all of these into component form, because from there, it's a hell of a lot easier. So let's write all these out in component form. So the first distance here is in component form will simply be 7.00 I and kilometers. That's because we're just going east, I'm just going 7 kilometers east. So D2, that's also nice and easy. That'll have no I component, and it'll just be 4.10 J kilometers. D3, we don't know. I'm going to write that over here. Let's use all the space available to us sensibly. And D4, so D4, I am given the fact, I'm told that we went southwest. So it's not as simple as these were to find, and instead I'm going to have to do some trigonometry. So let's come over here again, working out part 4 in component form. So I know that this is 45 degrees here, and this is 9 kilometers. Let's draw this out a bit nicer. So to find the I and J components, then the I component will just be 9 times the cosine of 45, and J will be the 9 times the sine of 45. Any math teachers will be realizing that these are in fact the same. Cos of 45 is equal to the sine of 45. Just an interesting little note there. So you know, the magnitude of these will be 6.36 kilometers. However, we need to take into account the distance because we're talking about displacements here. I've got to make sure I include vectors on all of these. Oops, that's my mistake. So the I component, we are heading in this direction, which is negative, and we're heading down, which is also negative. So in fact, D4 is negative 6.36 I minus 6.36 J. Okay, so now I can rewrite out this equation here with these numbers here. So I get D1, oops, better write it out with numbers if I'm going to do that. I have 7.00 I plus 4.10 J plus, I'm not going to bother putting a plus there, it's going to be minus 6.36 I minus 6.36 J plus D3 equals 0. So you can see here, I can just rearrange this for D3. So rearranging this and grouping together the components, so grouping this I, and this I, and this J, and this J, we end up as D3 is equal to 0.64 I plus, I should say minus, so I can group this together, these together, and this, then I end up as D3 equal to negative 0.64 I plus, not 0, 2.26 J. Okay, so this tells us D3 into this distance here in terms of in component form. Oops, that should be an I, not a J. Okay, so we can see actually that this, what I've drawn is incorrect. It should have been drawn, I'll draw it in purple, minus 0.64 I, so 0.64 in this direction, and then plus 2.26 J. So really it should be about here, and then this would be like that. Just a little bit interesting just to see how, even though our diagram was a bit off, we can still solve the problem. So this is good, but it doesn't actually tell us how far they went or what direction they turned in. So for how far they went, we just need to find the magnitude of this. We can just do this using Pythagoras. So the magnitude of D3 is just square root of 0.64 squared plus 2.26 squared. And that is equal to 2.35 kilometers. And now we want to know what direction they turned in. So for that, we want to find the bearing. So if I draw this here, see that it's going to be a bearing that goes all the way around and then back to there. So it's probably going to be easiest if I find out this distance here. So I think I'm going to once again have to erase a bit of this. I'm going to erase this information here. Okie dokie. Get rid of that as well. Okay, so let's redraw out our D3 here. We know this distance here is 2.26. This distance here has a magnitude of 0.64. So if I want to find this angle here, then I can just use the tan ratio. Call this angle here alpha. So alpha is equal to inverse tan of 0.64 over 2.26, which is equal to 15.7 degrees. So that means that the bearing will be given as, delete this down here and rewrite it out a bit nicer, I think. A bit nicer. The bearing will be given as 360 minus 15.7, which is 344.3 degrees true, or to three significant figures, 344 degrees true. So let's write it down here. Therefore, they traveled was 2.35 kilometers after turning 344 degrees true. So with question 8, we are moving into relative motion. Let's look at my pen working. Excellent. Okay, so we have a boat crossing a river that is 1,800 meters wide. We are given the velocity of the boat relative to the water, and we're given the velocity of the water relative to the shore. And we're also given a nice little diagram that shows us this information. Okay, so first of all, I always find it difficult to keep my relative to what's straight in my head. So I need to remember that B, anything with the subscript B is boat. Anything with the subscript S is the shore. And anything with the subscript W is the water. And I'm also going to draw a little diagram here. So here is my diagram. This is, once again, not to scale. So I know that the distance between the two banks is 1,800 meters. And I know that I've got a little boat here. I'll try to draw small, so it's maybe to scale, maybe a bit more to scale. I know that the velocity of the boat relative to the water is just going, it's directed perpendicular to the bank, and it's 4.0 meters per second. So I'm just going to write that over here. So V B rel W, 4.0 meters per second. I'm just going to put perpendicular to shore. I know that the velocity of the water is 2 meters per second, and that's parallel to the shore. So we've got the water coming through here at 2 meters per second. So you can see in this diagram, it kind of shows you how we're going to add up the velocity of the boat relative to the water and the water relative to the shore to find the velocity of the boat relative to the shore. So that's what we ultimately want to find. So we know that the boat is going to be traveling up this way, but the water is also going to be pushing it this way. And we're just going to assume that the boat is moving as fast as the water in the horizontal direction. There's a whole lot more that would go on in real life, but we're just going to pretend that that's the way that it works. So this means that the actual velocity of the boat relative to the shore is going to actually be angled something like this, because it's going to be moving horizontally thanks to the water and then vertically thanks to the engine of the boat that is trying to make it just cross the river. So this means that actually, if we see in our little drawing there, we get that this is the velocity of the water relative to the shore. This is the velocity of the boat relative to the water. And so we get that the velocity of the boat relative to the shore is the vector sum of these two. Boat relative to the water. So you can also see, if you look at this, that it's almost like these two W's here cancel. So we've got boat relative to water, water relative to shore. It's like these two cancel out, and we see we have boat and shore. So that's just another possible way of looking at these things. So because this is a vector sum, we need to add them vectorially. And happily enough, these will be perpendicular because we're told this is perpendicular to the bank and this is parallel to the bank. So to find the magnitude of the velocity of the boat relative to the shore, we can just use Pythagoras. So just draw a little line under here, because this is all information that we know, and this is all going to be information we'll find out. So velocity, magnitude of the velocity of the boat relative to the shore is just going to be the square root of 4 squared plus 2 squared, because we use Pythagoras. So square root of 20, which is 4.47 meters per second. So this is just 3 significant figures because we're just given 3 significant figures in the question. So now we need to find the angle. Once again, we can just use trigonometry as we have been. So looking at this, we have the horizontal and the vertical components. That means we're going to be using tan. So I'll skip most of it and just go, the angle will be given by the inverse tan. We're finding the angle to the shore. So the angle to the shore will be given by the inverse tan of the velocity of the boat relative to the water. So 4 over the boat relative to the water relative to the shore, which is 2, which comes out as approximately 63.4 degrees. So for question A, we can answer, well, velocity of the boat relative to the shore, it's traveling at 4.47 meters per second, directed at an angle angle 63.4 degrees above the shore. There we go. Okay, so part B is asking us about the time it takes for the boat to cross the river. So this question is actually quite simple. In fact, we already have everything we need in this question here to calculate the time. So the time it's going to take to cross, we have the velocity, and we've got to find the time. Velocity is distance over time, so we just need to know the distance. So we know the vertical velocity of the boat. So, well, not vertical, actually, I shouldn't say vertical. We know the velocity of the boat perpendicular to the direction of water flow. We know that velocity is just the velocity of the boat relative to the water, which we're given. And we also know that distance. That distance is 1,800 meters. So if I want to calculate how long it takes the boat to cross the river, I can just go, well, time as you'll see in the next module with particularly with projectile motion, time is a really nice way of converting between different components. So before we were working, if you want to change between working in one component and the other, the time variable is a really good way of doing that, because time is the same, at least if we're talking about Newtonian mechanics, time is the same in all of these different relative frames. So I can just go, well, the time is equal to the distance, perpendicular distance, divided by the perpendicular velocity. So that would just be 1800 meters divided by 4, which is 450 seconds, or to put it in minutes, which isn't necessary, but it makes a bit more sense, 7.5 minutes. So that's how long it will take the boat to cross the river. Okay, so question 9. Make sure I've got my pen on. Okay, so in this question, we're told that relative to the ground, a car has a velocity of 16 meters per second directed due north. And then we're told the velocity of a truck relative to this car. And we want to find out what the velocity of the truck is relative to the ground. As well as that, we're also asked how long would it take the truck to travel as far north as the car travels in 1 hour. So we're just going to leave that second part of the question for now, and we're going to focus on the first bit. So first of all, let's write out what we know. We know the velocity of the car relative to the ground is equal to 16 meters per second north. Just going to write N for north. We know that the velocity of the truck relative to the car is 24 meters per second north, 52 degrees east. So that means that what this form of bearing is going, well, we face north and then we turn 52 degrees east. So it would be there where this angle here is 52 degrees, and then that would be east. And that's okay, so let me just rub out this little diagram. So we can see here that if we want to find the velocity of the truck relative to the ground, we can sum vectorially the velocity of the truck relative to the car, and then the velocity of the car relative to the ground. In the same way as last time, to find the velocity of the boat relative to the shore, we summed the velocities of the boat relative to the water and the water relative to the shore. It's the exact same principle as we did last time. Just this time, instead of it being perpendicular and parallel to the shore, we're dealing in terms of coordinates north and north 52 degrees east. So T rel C plus V C. I'll rub that out and rewrite that in an attempt to look neat. C rel G. Okay, so drawing this out, I can go 16 meters per second north. So that's C rel G. Because I'm only dealing with velocities, I'm just going to label it like this. And then this is T rel C. And I want to find this here, which is T rel G. I'll just make these join up there. Okay, so first of all, let's write down what we know in this diagram. So that's 16. This is 24. And now this angle here, we know this here, this little angle here is 52 degrees, which if we now remember some fancy angle tricks, if I draw a line through here, then we know that this, between north and east, this angle here, which I'm going to use a different color, I'm going to use blue, this angle here is 90 degrees. So that means if this is 52, then this angle here, that has to be 38 degrees. Now, seeing as this angle in here is also 90 degrees, then this whole thing here, this big angle, is, and I'm going to write this in black because it's very relevant, this whole angle here is 128 degrees. So from all that we've done so far, you should be looking at this and going, well, I have one side of a triangle, I have another side of a triangle, and I have an angle in that triangle, and I need to find a third side. What does that make me think of? I know, the cosine rule. So the cosine rule is, of course, a squared equals b squared plus c squared minus 2bc cos a. And here, let's write it in red. This would be side b, this would be side c, and this would be side a, because this is the side that we want to find. We want to find the train relative to the ground. And so the angle opposite that would be this angle here. So this would be angle capital A. So plugging in these values, we get 16 squared plus 24 squared minus 2 times 16 times 24 times the cosine of 128 degrees. Once again, make sure your calculator is in degrees and not radians. You see that that ends up as approximately 1,305 meters per second, but we want to find the square root of that. So in fact, A is 36.1 meters per second. And this is to 3 significant figures, because we see here we're given this to 3 significant figures. I didn't actually write out this properly. This is actually 52.0 in the question, so this should be 3 significant figures too. Okay, so now that I've found the magnitude, it's time for us to find the direction. So here we were given the velocity of the truck relative to the car in terms of north 52.0 degrees east. So it makes sense for us to give the velocity of the truck relative to the ground in the same way. So this means that we need to find this angle in here, which I'm going to call angle alpha. So now we need to find an angle in a triangle that is not a right angle triangle. So unfortunately, we can't just use our normal trigonometric rules. Instead, we have to think and go, well, we've already used the cosine rule. Let's bring in the sine rule. We could, of course, do this using the cosine rule. However, I think the sine rule is a little bit easier in this case. So we'll go with that. So you can go sine alpha over, what's the opposite side? 24 is equal to, and we can use this angle here and this side, sine of 128 over A, which is 36.1. So alpha is equal to the inverse sine of all of this. If we just do some quick algebra that you can check for yourselves, 128 for 36.1, and that is equal to 31.6 degrees, which I think is quite satisfying. So this means that therefore the velocity of here, velocity of the train relative to the truck relative to the ground is equal to 36.1 meters per second north, 31.6 degrees east. Okay, cool. So now let's have a look at the second part of the question, which is how long would it take the truck to travel as far north as the car travels in 1 hour? So this is a bit of a confusing question on the face of it, so let's unpack it. So what we want to find out is how far the car will travel in 1 hour, how far north the car will travel specifically, and then we want to find out how long it would take the truck to travel that same distance. But not just that same distance north. Because remember, the truck's velocity is not all directed north, it's north 31.6 degrees east. So if we want to find out how long it will take how long it will take the truck to travel a certain distance north, we need to find the northern component of the velocity of the truck. It's a bit complicated, but hopefully it'll make sense as I step through the maths of it. So first of all, we need to figure out how far the car will travel in an hour. So we're given its velocity in meters per second. So that means we need to either convert this from meters per second to kilometers per hour, or we can find out how many seconds in an hour and then go from there. But I think it's easier to just convert this from meters per second to kilometers per hour. So the trick to converting from meters per second to kilometers per hour is to multiply by 3.6. So multiplying by 3.6, 16.0 times by 3.6, you end up with 57.6 kilometers per hour. And so this, of course, is 57,600 meters per hour. So to figure out how long it's going to take the truck to travel 57,600 meters north, we need to find out how fast it's going north. So with this, we can just use simple trigonometry. I'm going to switch again back to the blue color. So we can see here that the truck is traveling this direction here. And I want to find the northern component of that. So that would be this component right here. So we can just use trigonometry to do that. We can see, as we have done many times in the past, finding the northern and eastern components. It's simply the northern component is just equal to T-RL-G N is equal to the velocity itself, so that's 36.1, multiplied by the sine of this angle here, or the cosine of this angle up here. So through our angle rules, we know that this angle up here is equal to this angle down here, which is 31.6 degrees. So that's 36.1 times by the cosine of 31.6 degrees, which is equal to 30.8 meters per second. North, of course, because we're just talking about the northern component. So now we know how fast the car is going, how fast the truck is going north. We know how far it has to go, so finding the time is simple. Velocity is distance over time, so that means that time is distance over velocity, which in this case is 57,600 meters divided by 30.8, which comes out as 1,870 seconds, which doesn't really mean much, so let's convert it to minutes, and that's 31.2 minutes. So in the time that I just need to get my head straight around this. Sorry about that. So the car will take an hour to travel 57,600 meters north, but the truck will only take 31.2 minutes to travel that same distance north. I hope that makes sense. This one was a bit of a mind-bending one. It's a bit confusing. Feel free to leave any comments below if you want me to try to explain it again in a different way, or if you need me to clarify anything. Okay, so finally, finishing up with question 10. Well done if you've been watching this whole video, and hello if you're just tuning in for this one question. So we're told that a person looking out the window of a stationary train notices raindrops are falling vertically down at a speed of 5 meters per second relative to the ground. Then when the train moves at a constant velocity, the raindrops are making an angle of 25 degrees to the vertical when they move past the window. So how fast is the train moving? Okay, so our reference frames, or what we'll be finding our velocities relative to will be the ground, raindrops, and the train. So I'll just be using G for ground, R for raindrops, and T for train. Okay, so let's just draw this out quickly. So this is our train window here. It's a bit of a Dr. Seuss train there, I think. So we know that they're traveling vertically down at a speed of 5 meters per second. So when the train is moving at a constant velocity, so the train's reference frame is now moving, their raindrops make an angle of 25 degrees. But we're not told how fast the raindrops are moving down. We're just told this, and then we're just asked how fast is the train moving. So this may seem at first like we're not given enough information to find the answer, but if you see this diagram here, you should look at it and go, well, this is a right angle triangle because I have the vertical component of the motion of the raindrops. So this would be VR rel t, because the velocity of the raindrops relative to the train. This here is the velocity of the raindrops relative to the ground. And then what would this component here be? So if we go back to our relative motion equation, we think, well, the equation that we see the most often is, for example, V of A rel C is equal to V A rel B plus V B rel C. So I know that VR rel T is equal to VR rel G. That's this component. And so this component must be, to end up with this, vector signs here so we don't get confused, plus VG rel T. So what does this mean? This means this is the velocity of the ground relative to the train. So that seems like a bit of a weird thing to say, the ground relative to the train, because we know that the ground isn't moving, it's the train that's moving. But this isn't talking about what we physically, quote unquote, know is happening. This is just talking about what the velocity of an object from the point of view of the other. So we say, well, if I'm in the train, if I'm moving at a constant velocity, it seems like I'm stationary and everything else could be moving around me. So if you are in a car and your friend is waving goodbye to you, you're in the car, in there, then from your point of view, as you move forward, your friend seems to be moving backwards. But from your friend's point of view, you are moving forward. But from your point of view, you can think of it as your friend is moving backwards with the same speed. So the velocity of the ground relative to the train, the G rel T, is actually equal in magnitude to the velocity of the train relative to the ground, just in the opposite direction. So negative V T rel G, but their magnitudes are the same. So the question asks us how fast the train is moving. So we don't need to worry about the direction, we just want to know the magnitude. So we just need to find the length of this vector here. And because we have a right angled triangle here, and we have one side and we have one angle, we can just use trigonometry to find that. So if we look at this, we can see that this is this is just the tan ratio. We have the opposite over the adjacent. So in fact, I'm just going to call it T rel G is equal to 5 times by tan 25, which is just 2.33 meters per second. So that is how fast the train is moving. So if you have any questions from this tutorial, please leave them underneath in the comments on Open Learning. Probably Liz will respond, or I might, but let me know if you find any mistakes as well, and we'll update the video.